Hi everyone, we are in chapter 17. This is the first video in section 2, curved mirrors. By the end of this video, you should be able to draw diagrams or to draw array diagrams to find the image distance and magnification for concave and convex spherical mirror. Curved mirrors are also called spherical mirrors because they are parts of a sphere. You see that the concave mirror is this part of a sphere and we have a convex mirror. The figure shows the difference between both of them, convex and concave mirror. Convex mirror, it reflects from the outside, but concave mirror reflects from the inside. Concave mirrors can be used to form real images. A real image is an image formed when rays of light actually pass through a point on the image. Real images can be projected onto the screen, like what we see here. Before starting in the ray diagram, we need to know what's C, what is capital F, what's small f, what's R. C is the center of the curvature of the mirror. R is the distance from C to the mirror, which is the radius of curvature. Capital F is the focus, or what we call a focal point. Small f represents the focal length, which is the distance from F, of the focal point, to the mirror. The length of the focal length itself equals the radius divided by 2. If the object or the image is in front of the mirror, if we're going to measure the distance in front of the mirror from the left side, the distance is going to be positive. But if we are measuring behind the mirror, the distance will be negative. Also for the heights. If we are measuring above the principal axis, the height will be positive. If we are measuring below the principal axis, it's going to be negative. This is the principal axis, this line. When drawing a ray diagram for concave spherical mirror, draw the diagram to scale and mark the center of the curvature, C, and the focal point, F. The focal point is midway between C and the mirror. The first ray is drawn from the object to the mirror parallel to the principal axis. This ray then reflects through the focal point, F. The second ray is drawn from the object through the focal point. This ray then reflects parallel to the principal axis. The top of the image appears where rays 1 and 2 cross. These two rays are enough to locate the image. You can draw a third ray, however, to check. Start at the top of the object and draw ray through C. It will reflect back directly through C again. The image appears when the lines cross. If the bottom of the object lies on the principal axis, then so the bottom of the image. If the object distance is greater than C, and we draw the three rays we have learned, the intersection will be here. After drawing the image, we see that the image distance from the mirror is between C and F, and the height of the image is smaller than the height of the object. And the object is real, inverted, and smaller than the object. If the object's distance equals to the radius R, or the object is at C, and we draw only one light ray like this, the image will be formed at the same distance with the same height of the object itself. So the image is really inverted and the same size as the object. When the object moves closer to the mirror and we draw the ray diagram, we will find that the image is going to be formed at a distance greater than C. And the image is greater in size than the object itself. So the image is larger, real, and inverted. As the object approaches the mirror, when it reaches at a distance equals to the focal length, the reflected light rays are parallel. They will never intersect. At this point, there is no image formed. Finally, when the object is at a distance smaller than the focal length, the reflected light rays will move away from each other. They will never intersect in front of the mirror. So we draw extensions like this one and this one. Their intersection will be behind the mirror. So the image is going to be formed like this. It's going to be upright, greater than the object and virtual, not real. Again, to summarize, this is the object, this is the image form, these are the light rays. So when the object is moved toward a concave spherical mirror, its image changes. For object distances greater than the focal length, the image is real and inverted, which means upside down. As the object moves closer to the mirror, the image appears farther away. This continues until the object is at the focal point. At the focal point, as we said before, there's no image appear, or the image appears infinitely far away from the mirror. We cannot see any image. When the object passes through the focal point and lies between the focal point and the mirror, the image formed behind the mirror, just as it does for an ordinary flat mirror. The image is now virtual and upright. The light leaving the mirror appears to originate from here, even though it actually comes from here. A convex spherical mirror is a mirror whose reflecting surface is outward curved segment of a sphere. It reflects from the outside, as we said before. Light rays diverge upon reflecting from a convex mirror, forming virtual image. This is always smaller than the object, as we see from these two examples. To find the size and the location of the image produced by a convex mirror, you will draw the object, the mirror, and the focal point. The focal length is negative, as the focal point is located behind the mirror. Ray number 1 begins at the tip of the object. It travels to the principal axis, or it travels parallel to the principal axis towards the mirror. The ray will reflect backward and at an angle as it originated at the focal point, as it comes from here. Ray number 2 begins at the object, travels directly toward the focal point. It then reflects back parallel to the principal axis. The reflected light ray 1 and 2 will never intersect in front of the mirror, so we draw dotted lines like this, and these lines extend the path rays 1 and 2 backward. The dotted lines are light rays that are reflected from the mirror. At the point where the dotted lines cross, the virtual image appears. It's upright and smaller than the object. If you look here, it doesn't matter where the object is. As long as it's in front of the mirror, the image will always be smaller, virtual, and upright. There are 2 worksheets attached to this lesson in Coursera's course material. Make sure to answer these questions. And if you have any question, feel free to ask me during the Coursera discussion rooms. Thank you.